Okay, so here are the notes for section 3.6, the mathematics of finance. So we've got two kinds of interest. You have simple interest because it ignores the effect of compounding. The interest charge is based solely on the original principal, so interest is paid, or interest on interest is not included. Compound interest is interest charged based on the original principal plus any interest on accrued interest, interest earned on interest itself. So compound interest would be, if you're, say, for example, compounding monthly. So you would earn some interest at the end of January. But when you go to calculate the interest for February, you don't have your original amount, you have the original amount plus the interest. So you're earning interest on your interest. Simple interest would be you just calculate it once at the end of the year, things like that. So here's our formula for compounding annually. The amount of money in the account is equal to the principal, 1 plus R, where R is the interest rate, and then N is the number of years that have passed. So it says, suppose George Milligan invests $5,000 at 5% annual simple interest, and Quan Lee invests $5,000 at 5% annual compound interest. Compare the values of both investments after 10 years. So what's going to happen is, so for George here, so the amount of money in his account is equal to the principal, $5,000, 1 plus the interest rate is 0.05, and then it's going to go for 10 years. So that's a relatively straightforward calculation. So let's see here. I feel like I'm doing this question wrong. Oops. I actually think I'm finding Quan Lee's. We'll find out. Oops. 1.05 raised to the 10th. So this comes out to be 8144.47. Okay, yeah, this is actually Quan Lee's here. Interest on interest. At the end of each year, so compounded interest. So suppose George invests $5,000 at 5% annual simple interest, which means he's only earning interest on his principal. So we'd have to find 5% of 5,000. So this is George. So 0.5 times 5,000. Whoops, I did not 0.5, 0.05. I did 50% interest. So he's making, so this is his interest George is making. George makes $250 interest times 10 years. So the total interest he earns is going to be $2,500 for a final balance of $7,500. So Quan Lee here comes out ahead because he's earning interest on his interest. All right, so interest compounds K times per year. So here's our formula. So similar variables, A is the amount of money in the account, P is your principal, 1 is the number 1, R is your interest rate as a decimal, K is the number of compounds per year. So quarterly, for example, would be 4, monthly would be 12, biannually would be 2, weekly would be 52, daily 365, and then T is the number of years. All right, so suppose Roberto invests $500 at 9% annual interest compounded monthly. Find the value after 5 years. So A is equal to the principal, 1 plus 0.09, the interest rate as a decimal. Our monthly, so our K value is 12, and our exponent is going to be 12 times 5. Now, these are all numbers. You can literally type that entire string into your calculator, and it'll spit the answer out all at once. So 500 times 1 plus 0.09 divided by 12 raised to the 12 times 5. Notice you do need parentheses around the stuff in your exponents, unless your calculator lets you type in the exponent. So Roberto here will have $782.84. Remember, this is money, 2 decimal places. Okay, Judy, $500, 9% interest rate. How long will it take for investment to grow to $3,000? So we're going to solve this problem, except we know our A value. So 3,500, 1 plus 0.09 over 12, and it's going to be 12 T, so I'm solving for the time. So we can divide the 500 across, so that's 6. 1 plus 0.09. Well, here, we'll do this. So what I would do next is I need to work out what actually I don't need to work that out. I need to get this out of the exponent, which means I need to take the natural log of both sides. Now you could use the common log, it doesn't actually matter. So you'd have that. Now I would need to divide the 12 and the natural log across to get t by itself. So what that looks like is this. Whoops. 1 plus 0.09 over 12. And then this is whatever t is going to be. So the natural log of 6 divided by 12 divided by the natural log of 1 plus 0.09 divided by 12. T is equal to 19.98 years, so about 20 years to get all the way up. Now, if you wanted to, you could turn these all into decimals at any point in time. The longer you wait to convert to decimals, the more exact that value will be. All right, 4, Steven's got $500 to invest. What is his interest rate compounded quarterly? If he wants to double his money in 10 years. So if he starts with 500, our goal is $1,000. 1 plus, I do not know the interest rate. We're doing quarterly, so 4. So 4 compounds over 10 years. So I can divide the 500 across. So 2 is equal to 1 plus r over 4 to the 40th. So I would need to take the log of both sides. So this becomes ln 2 equals 40 ln 1 plus, so it look like this. Okay, so I'm going to divide that across. So ln 2 divided by 40, that's 0.0173 equals a natural log of 1 plus this. So I have that. Now I need to undo the natural log, so everybody becomes exponents on the e. So e to that number that I just found is 1.017, and that's equal to 1 plus r over 4. So subtract the 1 across, 0.017 equals r over 4. Multiply everybody by 4. Oops. Minus 1. Forgot to subtract 1 divided by 4. So r is 0.0699. So that would be about 7% interest rate. If you wanted to double his money in 10 years, compounding quarterly. Okay, compound interest. So if you calculate interest continuously, this equation actually collapses to this equation is related to a limit we had in a previous section, but it's similar. So suppose Latasha invests $100 at 8% compounded continuously. So we're using this equation. So A equals her principal, E, her interest rate is 8%, so 0.08 times T. So we have to do 1 here. So that we'll do. So when T is 1, when T is 2, we're going to skip all the ones in the middle, go up to T is 7. So 100 e to the 0.08. So for the first year, it's just that. So she, at the end, has, the first year has $108.33. After 2 years, she has $117.35. So first year she made $8 in interest. The second year she made $9 in interest from 1 to 2. If we go all the way up to 7, let's plug 7 in for T, she's up to $175.07. So it's growing pretty quickly. All right, annual percentage yield. Common basis for comparing investments is the APY, the percent rate that compounded annually when you yield the same return as the given interest rate in the given compounding period. So when you see a bank or an investment, even if they may be compounding the interest quarterly, monthly, whatever, they will usually give you an annual percentage yield. So if we were just going to calculate interest once at the end of the year, this is what it would be. So Ursula invests $2,000 with Crab Key Credit at blah, 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 compounded quarterly. Okay, so we're going to figure out how much she ends up with and then work backwards to get it back. So A equals 2,000 1 plus 0.0515 quarterly is 4. And then this is just going to be 4. That because our t is 1. So that's all numbers. That can all just go straight in my calculator. So 2,000 times 1 plus 0.0515 divided by 4 raised to the 4th power. So at the end of the year, she has $2,105. So I'd figure out how much money she'd make if we were not compounding. So the amount of money in the account is equal to the principal 1 plus r to the n, which is just going to be 1 year. Actually, this is going to be, whoops, but we know that number. That number is 2105. So let's see here. So this will become 2105 is equal to 2,000 plus 2,000r. I can distribute because the exponent is just 1. So subtract the 2,000 across. Now divide everybody by 2,000. So 105 divided by 2,000 is 0.0525. So the effective annual interest rate is 5.25%, even though the quarterly interest rate is 5.15. Usually the annual interest rate will have to be more than in order to catch up for the compounding. All right, so the last one here, or sorry, example 7, not the last one. Compare 8.75% annual interest compounded quarterly to 8.7 annual interest compounded monthly. So this interest rate compounded quarterly means that we are actually looking at, so our rate is that, so compounded quarterly, so A equals, doesn't actually matter what number we have, so we'll just put, we'll say we're going to invest $100, 1 plus 0.0875 divided by 4 quarterly, and then 4 times 1, we'll do it for 1 year. Over here, same amount of money, plus 0.087 divided monthly, so to the 12th. So these would be your two, so 2 times 1, we should do in 1 year. So the one on the left, if we compound quarterly at 8.25% or 8.75%, 100, 1 plus 0.0875 divided by 4 raised to the 4th. This one would come out to be $109.04. So you've made, the interest earned is $9.04. Over here, so 100, 1 plus 0.087 divided by 12 raised to the 12th power is 109.06. So the amount of interest earned in this case is $9.06. So even though this interest rate is slightly lower, now the longer I let this run, the more different these numbers would be. I only did 1 year, so the difference is only 2 cents. But if you went up to 100 years or 10 years or 1,000 years, like the numbers would get very, very different. So the lower, even though this is a lower interest rate, the compounding more than enough makes up for it. Okay, so we've got annuities, which deals with future value. So an annuity is a sequence of equal periodic payments. The annuity is ordinary if the deposits are made at the end of each period. At the same time, interest is posted in the account. So the future value of an annuity consisting of n equal periodic payments of r dollars at an interest rate of I per compounding period is given by this goofy formula. So at the end of each quarter, Emily makes a $500 payment into the mutual fund. If her investment earns 8 or 7.88% annual interest compounded quarterly, what will it be in 20 years? Okay, so the future value are periodic payments of r dollars, so that's how much she's putting in, so 500. 1 plus I is the interest rate, 0.0788. Oops, no parenthesis there. Well, actually, we'll leave one. We'll put a bracket there instead, so I need parentheses here. N is, let's see here, N equal periodic payments. So the end of each quarter year, so she's paying 4 times a year for, let's see here. So that's going to be N equal periodic payments. So how many payments is she making? End of each quarter, 4 per year for 20 years, so that's 80. minus 1 all over I, which is 0.0788, the interest rate. So we have that formula. Numbers go in the calculator, so we'll work the fraction part out first. So 1 plus 0.0788 is that, raised to the 80th, minus 1 divided by 0.0788 times 500. I feel like that's wrong. Maybe that should just be 4. Just make it 4 payments a year. No, 80 would be right. So future value, if she makes $500 appointments, so she's putting in $40,000. Given the interest rate and all that other fun stuff, the balance comes out to be $27,334. Nope, off by 1. $2,733,454.49. So, not bad. Saving $500 every 3 months. Now, granted, you're earning pretty high interest rate. You're never going to see that in real life, or probably won't. Okay, the reverse of this is a loan and a mortgage. So annuity is a sequence of equal periodic payments. The net amount of money put into annuity is its present value. The net amount returned is its future value. So present value, so here, the annual interest rate charged on consumer loans is the annual percentage rate. The APY for the lender is higher than the APR. So Carlos produces a pickup truck for $18,500. What are the monthly payments for a 4-year loan with $2,000 down payment if the annual interest rate is given by is 2.9%? So let's work this out. So of our dollars, so he only has to borrow that much. Do a bracket. 1 minus I feel like I'm doing this problem wrong. 1 plus the interest rates, 0.029 to the negative n. So monthly 4-year loan, so that's going to be 48 payments over 0.029. So let's work this out. 1 minus 1 plus 0.029 raised to the negative 48th divided by 0.029 times that. Well, that is definitely wrong. Let me do some research here real fast. All right, I found my mistake. So I actually made it on the previous problem as well. So the issue is this is an APR. I need to divide it by 12 since it's a monthly value. So this should actually be, I put the 16. So that is equal to R, because that's how much I need to pay. I wanted the present value to be the total. R is what I need to pay. So it's going to be 1 minus 1 plus 0.029 over 12, since I'm making 12 payments. And this is going to be raised to the negative 48th, because I'm making 48 payments total, divided by 0.029 over 12. The monthly interest rate. Now, there's a lot of algebra here. I don't particularly want to work it all out, so the R value comes out to be $364.49 would be his monthly payments in order to settle that debt. So the present value is the value that you have borrowed. You need to make R payments in order to get up to that. So the issue was on the previous problem. Let me grab it real fast here. Here, first of all, I needed to divide these by 4 because the interest rate is compounded quarterly. So I have to convert it back into the, how much would be earned per quarter by dividing by 4. So it actually comes out to be not some ridiculous number. It's not bad, but not that big. It's actually $95,483.39 would be how much money Emily would have at the end. Okay, which brings us now actually to the end of the section.